Okay, so let's start the lecture of today. So this, there are several other remaining surveys, and feel free to continue working on the survey, and they'll grab the remaining surveys. So today's lecture is going to be mainly about clarification of the terminologies. So we will clarify the terminologies differences between the transformer encoders and decoder, and also the tokenizer versus tokenization. And these are some, and there is also the difference between tokenization and the modeling. So these are some key features of Hugging Face model. After today's lecture, you will be able to start working on assignment 3. So yeah, let's start. This is a reiteration of the edits you need to update for the starter code in assignment 3. In this script of the test function, please change the args.use CUDA into args.use GPU. So this was a typo in the starter code, and in order to correctly run the code, you need to change this line into use GPU. So there's another update for the package, but this package is already installed in the CS server now. So if you run the script of the assignment 3, there should be no problem with this package anymore. So as a recap, let's briefly take a review of the sentiment analysis problem. The sentiment analysis is formulated as a sequence-based classification problem. So suppose you are building a model and you give the model a string, and this string can be a sentence, a few sentences, or paragraph, or a few paragraphs. The length could be different. The goal of this problem is to let the model predict if this string contains positive or negative or sentiment about the movie. In this example, you can see that this review is positive. So it says that the story of this movie is a good story, and the story unfolds flawlessly. The acting is without fault, and the cinematography likewise occasionally quite brilliant. And overall, the movie is warm and not excessively sentimental. The goal of the sentiment analysis task is to predict if sentences like this kind of movie reviews are positive or not. The model we're going to use is a deep neural network-based language understanding model. So we take a pre-trained language model and fine-tune them on the sentiment classification task. And the IMDb movie review task is called the downstream classification task. And we let the model predict if the review is positive or not. So the Hugging Face transformers provides a convenient workflow for building deep neural network-based language understanding systems. So after last lecture, some students asked me about the difference between embedding-based system and the deep neural network-based system. So there are a lot of overlaps between these two types of systems, but there are still some key differences. So for the embedding-based language understanding systems, the embedding handles all of the understanding of the language. But in deep neural network-based system, the whole system, which are essentially a massive deep neural network, contributes to the understanding of language together. And as of 2023, most of the systems that you go out to see are based on deep neural networks. So almost all the networks, almost all the systems that you can see are based on deep neural networks. Question?
So can you please repeat what do you mean by downstream task data? So is this the same raw input text that we're entering, or is it some other result of some other task that we complete?
So downstream is just used to contrast to pre-training. So by pre-training, you're feeding the language model with essentially all the available data on the internet that you can acquire. For example, Wikipedia or Reddit or even some human label data. But for the downstream data, an example is the movie review classification. So whatever you want the models to do, you can fine-tune this model on the downstream task data. So the downstream task data should be as similar to the deployment scenario as possible. So if you want this model to predict the sentiment of the movie review, you fine-tune them on the movie review data. Okay, next question.
Can you give us one example of just embedding-based networks like GPT and BERT can be example of DNN-based, right?
GPT and
one example of that.
yeah. So both BERT and GPT are deep neural network-based systems. And an example for embedding-based system is GloVac plus conditional random field.
But even in that case, we take the embedding and then we apply some neural network and get the final result, right? So that serves as the initial embedding, but we still have a deep neural network, right?
So technically, there are some overlaps between the actual building of these models, but when setting up these models, actually probably GloVac plus CRF is not really a best example for embedding-based system. A better example is to take the average of the embedding and just pass them through some threshold. So there's no neural networks out there in the GloVac plus taking the average, computing the cosine similarity, and passing through some threshold and make the predictions. So that would be an embedding-based system. Okay, thanks. Any other questions about the types of natural language understanding systems? Okay, great. Let's take a look at the overview of the pipeline. So usually in the Hugging Face setting, the system contains two parts, a tokenizer and a BERT for sequence classification model. So you can use other models other than BERT, and in that case, the model's name will be, for example, Roberta for sequence classification, or Albert for sequence classification, or GPT for sequence classification. And Hugging Face actually provides some flexible classes named AutoModel for sequence classification. You can instantiate these models using the corresponding names of the models that you want to use, and use them accordingly. So in the next few slides, let's take a look at the tokenizer. Tokenizer is a crucial component of natural language processing systems. So it encodes the text into numbers. Texts are not able to be directly processed by computers, but numbers can. So computers operate on numbers, but we humans operate on symbols, and texts are symbols. So we really need the tokenizer to encode the text into numbers. And according to the Hugging Face definition, the tokenizer does the encoding process. So this encoding process actually contains two steps, tokenization and the converts tokens to IDs. The tokenization step just splits the sentence into the sentence, which is a string, into a list of tokens. And the definition of the token will be visited in the next few slides. Question?
Actually, in the starter code for assignment 2, which was already like deep neural network based, there was just like this simple tokenization without any stemming, lemmatization, without any attempts to assign text to tokens. So is it still typically done in deep neural network based systems, or do people just like discard these approaches and just assign a number for every different token without trying to process the words themselves?
Assignment 2 is a deep neural network-based system. So
yeah, but I mean, in real life, do people still do stuff like stemming and lemmatization?
In real world, most people are doing the byte pair encoding, which is a type of subword encoding, and I'll actually describe that in a few slides. So the subword tokenization has some benefit compared to the word tokenization or the character-based tokenization. So there are some trade-offs between the number of the sizes of the vocabulary and the length of the sequence. So subword tokenization has some benefits. And yeah, So the encoding part is done by the tokenizer, and the tokenizer encoding process contains tokenization and the converts tokens to IDs. And these two steps are actually the function names in the Hugging Face Hugging Face transformer toolkit. And I will also show some coding examples in the next few slides. And of course, the reverse of this procedure is called decoding. So there are a lot of choices to do the tokenization. And the most obvious choice is to do the Python split. You can just call the split, and by default, this function splits the words according to spaces and new lines. So after that, you can look up each word in a dictionary, which is the vocabulary, and you can use the index in the vocabulary to represent the word. And the drawback of this kind of approach is that the words with the same lemma forms are considered as different words. So convert should be almost the same as converts, but it is considered very different words, just as converts versus splitting, or converts versus tokenization. And also the punctuations are not handled well. So let's say in the end of the sentence shown in this box, there is a punctuation mark. And if we just do the Python split function, then the sentence start is considered one word. And this word will appear different from sentence, which is, again, undesired. So how to fix this problem? We can separate the punctuations out. You can detect the punctuations and split them into some standalone tokens. So in this way, every single token is a token that does not contain the punctuations. And then you can continue with looking up the word in the dictionary and use the index to represent the word. So now you effectively convert the token into the numbers. But the drawback of this approach is that the size of the vocabulary is still unnecessarily large. And for example, in English, many words have the same part of the word, like geography and bibliography have the same root. They all end with graphy. And this kind of common components in the words carry some meanings. And if we just do the word-based splitting, then this kind of similarities between the words are not captured. So another another problem is that nowadays the natural language processing systems require processing of multiple languages, like English, French, Chinese. Across many languages, there are some words that are shared. Actually, there are only part of the words are shared. For example, English and Latin, there are a lot of words that a lot of English words actually come from Latin, but the actual forms of the words are different. So in method 2 tokenization, even if we handle the punctuations well, these kind of problems are still remaining. So we really need better methods to do tokenization. And method 3 is character level encoding, or the byte level encoding. In lecture 7, you have seen an example of this. In the Canine model, they did the character or byte level encoding. So in this method, you essentially split every single character into the same into a standalone token. So by splitting out every single byte, the vocabulary size is going to be significantly reduced compared to the previous method. So the previous methods, you need to handle like tens of thousands of words in the vocabulary. But here you only need to handle several hundred items in the vocabulary. So the vocabulary size is going to be significantly reduced. And a benefit of the reduced vocabulary size is that in the generation, your search space is going to be a lot narrower. But at the same time, the search space is also going to be a lot deeper because you need to handle a much longer sequence. So, and also, most NLP systems are notorious at handling the long sequences. So, if some pieces of information are spread along the very long sequences, it's going to be very hard for the NLP models to assemble the knowledge, the information pieces back together. So we really need to strike a balance between the character level encoding and the word level encoding. And this is the motivation for finding a subword encoding. And the subword or so-called word piece tokenization is adopted by many popular language models, including BERT and GPT, so GPT-2, GPT-3, and even GPT-4, which were just released yesterday. And in the subword tokenization method, they find some words and find some locations to split those words. And the heuristics of finding this kind of words are mostly based on the frequencies of occurring in some particular corpora. And every single developer of different language models use a set of different heuristics. And the actual heuristics are outside of scope of the CSC 401 or 2511. But also because every single model uses their corresponding tokenizers, which when we use this type of language models, we should also use their corresponding tokenizers. So if we use burst tokenizer and pass it into the GPT model, then the GPT model is not going to understand anything. So we should use burst tokenizer and when we are using the BERT model. So here's an example of loading and using the tokenizer. Hugging Face Transformers has the auto class, and on this slide shows an example of the auto tokenizer. So here the auto tokenizer allows us to select a model, and here the name of the model is BERT-base-cased. So you can just call auto tokenizer.from pretrained BERT-base-cased and get the tokenizer that was built. And this tokenizer actually includes the heuristics to select the words to split and where to split. And also this comes with the vocabulary. So when using this tokenizer, you can just pass in a string which contains an untokenized sentence. And this tokenizer does the two-step encoding. So the outputs are a collection of numbers. For example, the input IDs and the attention masks. So currently, the attention masks are all ones. This is going to be very useful if you are handling a batch of sentences. So in a batch of sentences, you want to pad the shorter sentence to have the same length as the longest sentence in the batch. So for the padded tokens, usually the attention mask is going to be 0. And inside the transformer models, if your attention mask is 1, then it's okay. But if your attention mask is 0, then this model zeroes out the attentions at the corresponding locations. So essentially, that padded token does not affect the semantics of the sentence. Question?
So here the input sentence has 6 words, but input IDs has 9 numbers. So I guess it did something like use and in, like split use
Yes.
into use and in, maybe something like transform and R.
Yes.
Yeah,
Some of the words are split, and you can use convert IDs to tokens to reversely query which tokens and this corresponding IDs correspond to. Question?
So in this case, they're splitting it up by morphemes specifically. Is this the most optimal way of splitting that?
Essentially, yes. They're splitting by morphemes.
Is that the state of the art today?
Yes. The WordP is the state of the art. Yeah. So, calling tokenizer with and passing in a sentence is equivalent to first calling the tokenizer.tokenize, and then calling the convert tokens to IDs. So in Friday's tutorial, I will also describe some details of using the tokenizers. So as a recap for the tokenizer versus tokenization, so tokenizer in Hugging Face actually does two steps. So tokenization, then convert tokens to IDs. So this is one of the two terminologies that we need to remember, and don't get confused by this type of terminologies. So let's take a look at the pipeline. Actually, the details of the pipeline will be described in Friday's tutorial as well. And today I'm just going to say that in the auto model for sequence classification class, the classifier is just a linear head. It's a torch.nn.linear. You're going to write that line in the assignment 3, classifier.py. And the pre-trained BERT is a so-called BERT model. And usually this BERT model contains 12 layers if it's a BERT-based model, or 24 layers, 36 layers if it has other sizes. So usually if we say a model is a BERT-based or a GPT-2-based model, then what we are saying that the model has size base, which usually means that this model contains 12 layers and something like 12 attention head, and the hidden dimension is 768, something like that. But if we just say a BERT model or a GPT-2 model, then this model could have 12 layers, it could have 24 layers, could have 36 or 48 layers. It is actually referring to a family of models that are built in a similar manner. So the BERT model is the encoder part of this transformer. So on the right-hand side shows the model structure of the transformer. The left part is the transformer encoder, and the right part is the transformer decoder. So we don't need to worry about the right part, which is GPT. We only need to worry about the left part in assignment 3, which is BERT. So the BERT model contains n layers. If, for example, in the BERT-based model, there are 12 layers of this block, and each block contains the multi-head attention, add unknown, feed forward, and add unknown blocks. So this kind of the details for every single block is actually described pretty clearly in the Vaswani's paper. So when implementing the BERT model for assignment 3, please definitely check out and the multi-head attention is for example softmax of Q transpose K divided by the square root of dimension, and after that multiplied by the V vector. And the details of the BERT models are also described in lecture 7 and some of others deep neural network language models lectures. So as the takeaway of this slide is just that the BERT model is the encoder part of the transformer, while the GPT models are the decoder part of the transformers. Well, they are almost the decoder part of the transformers, but there are some slight differences. And some people would like to say encoder or decoder, and today I'm going to emphasize that the encoder and decoders words, this kind of terminologies are highly overloaded. They refer to very different things when they are talking about transformers versus sequence-to-sequence models versus the tokenizers. So it's very important to keep in mind which actual part they are referring to when they are mentioning the encoder or decoder. So I actually recommend against overloading the terminologies. So instead of saying encoder or decoder, it's better to just say BERT model or GPT-2 models. So any questions about this slide or the structures of BERT model? Yeah, question?
So just to clarify, when BERT was trained, it was a full transformer, but then once they trained it, they just threw away the decoder part.
The training of BERT is just the left part.
Okay.
Yeah.
So they never used the decoder in the first place, even during training?
No. So in the training of BERT, they are training on some pre-training task like the clause, just masking some tokens and try to predict what token that is, and also predict the next sentence. Or there's another. There are a lot of combinations of different pre-training tasks, and for the there's another key difference between BERT and GPT-2. So other than the unidirectional versus bidirectional connection, BERT has 3 embeddings, but GPT models only have 2 embeddings. So the BERT embeddings contain word embeddings, position embeddings, and the segment embeddings, but the GPT embeddings contain only the word and the position embeddings. So all of these details are you don't need to remember these kind of details in a model. The papers that describe how these models are trained are saying these kind of details pretty clearly. Okay, thanks. So for the review of this lecture, by the end of this lecture, you should be able to describe what is tokenization and tell the difference between tokenization and tokenizer. And then you should be able to describe a BERT for sequential classification system, which is a deep neural network-based language understanding system. And yeah, you can start working on questions 3 and 4 in assignment 3. And Friday's tutorial will also be helpful for doing question 3 and question 4 as well. So for question 2, not yet. We actually recommend using the speech brain option to do question 2. And speech brain is very similar to the BERT for sequential classifier. It's almost just a variant of the Hugging Face transformer, but for speech recognition. So I'll cover how to do the speech recognition next week. And also, if you have time, feel free to check out the demos by OpenAI for the GPT-4 model. I posted the link on Piazza. It's only 20 minutes. So yeah, that's the end of this lecture. See you on Friday.